Interestingly, recreating these parallel rays with a local light source isn't particularly difficult, as we can just use a lens. You see, when the lens is placed in front of the light at the lens's focal length, it actually collimates the light rays, which means that it makes them parallel. These newly collimated rays now have some of the characteristics of the sun, namely that the light intensity doesn't change because of distance alone, and shadows don't change in size either, which is super interesting to see. Another fascinating result is that anything at the lens's focal point appears to be pinned at infinity, and appears the same size no matter whether you're close to it or far away, as we observed in my recent DIY projector project. Anything at the lens's focal point appears to be pinned at infinity, and appears the same size no matter whether you're close to it or far away, as we observed in my recent DIY projector project.
I want you to notice the power lines move inward and lower to the ground the further they move out of your view. The same way with a long corridor or a hallway. And the same here with the street lamps. This is due to human perspective. And again here, notice how the railroad tracks merge into each other and then they eventually disappear and meet the sky at the horizon. And again here with the power lines, notice they move inward and downward until they eventually vanish out of your sight. As you can see from this point of view, the bottles are all lined up evenly. They're the same width apart and the same height. No fancy camera tricks here, just a phone camera. Now from this perspective, you can see that they all move inward and that they all get smaller in size towards the end of the table, and the table is flat. Now if the table were longer, these bottles would eventually disappear. That's called your vanishing point. Now the sun does the same thing. When you think you're seeing the sun set, you're only seeing the sun move out of your line of sight. That's called the law of perspective. As you can see here, the sun moves inward and gets smaller the further that it moves away from you. So the sun doesn't go over the horizon, it goes into the horizon. As you can see here, the street lamps are smaller the further away they are from you, and larger the closer they get to you. That works the same way with the sunrise. As you can see here, how much bigger the sun gets the closer that it comes to you. Now technically the sun does not get larger, nor does it get smaller. It only appears to get larger and smaller as it moves in and out of your line of sight. Just as you've seen the power lines and the light poles do. string is tied perfectly level across the counter, and the bottles are sitting level on the countertop. Now let's look at it from the same perspective. So as you can see, the sun doesn't set nor does it rise. It merely only goes out of your line of sight, moving beyond the vanishing point, just as someone walking away from you. Now, for example, as you can see right here, the field goal is at ground level and the bleachers are at ground level, but the man seems to be walking over a curve or down into the ground, but he is merely only walking out of your line of sight. The further he gets away from you, the less you see of him and the smaller he gets. Now, the closer he gets to you, you see more of him and he seems to get larger until he's right in front of you. And that, ladies and gentlemen, is called the law of perspective. Thanks for watching. Okay, I know you've been waiting for this. Now check this out. The clouds that look white don't show up in front of the sun because they're behind it. It's lighting them up. The clouds that are dark are on this side of the sun. That's why they look dark to you. Now, if you was on the other side of the sun, all these clouds that look dark to you on this side of the sun, well, they would look white to you if you was on the other side of the sun, just like these clouds right here on the other side of the sun that you're looking at right now.
look white because the sun is in between the clouds. The ones that are behind it are lighting up white, but the ones that are in front of it are dark, and you can see them pass through it right here in the negative filter, plain as day, and the solar filter. But the white clouds don't pass in front of it, do they? No, they don't, because they are behind the sun. It's lighting them up. It's not lighting the dark clouds up because it's on the other side of them. And you're looking at it from the dark side. It's really, really simple. Now, this is only possible one way. As you can see here, you have the white clouds behind the sun, the dark clouds in front of it. Now, check this out. I have a piece of cardboard box cut out. I have one side of it on the light bulb of the lamp and one side on the other. It means the sun would have to be located here in the middle to cast light on the clouds behind it. But it can't cast light on the clouds in front of it. It's really, really simple. Okay guys, one of the big questions I get about flat earth is, for one, how does the flat earth map work? It is, how do the seasons work? And also another question I get is, how come there is a 24-hour sun in the North Pole in the summertime and 24 hours of darkness in the wintertime? Well, it's really simple. Now, first of all, let me run over this with you really quick, because I got to get in bed and I don't have a whole lot of time. So I'm going to show you the map, which is patented on November the 15th, 1892. This is the version I have on my wall, but I took it off tonight so I can show you this really quick. As you can see, it's what, 10/4/1892. Okay, first of all, before I show you how this map works, what I want you to notice is over here to the right, you have the winter solstice, which starts on December 21st. Now, this right here in the center is the North Pole. Now, this little circle that you see right here with this illumination around it, that's the sun. Now, in the wintertime, the sun is out here. It's on its outer circuit, making its circuit around the earth. It's further out towards the ice wall. Okay, now in the summertime, which would be your summer solstice, which is on here called the June solstice, and it explains to you pretty much how that works. Okay, and I don't have time to show you. If you want to get really good detail, just order the map. But anyways, notice how the sun here is closer to the North Pole, making a smaller circle than it does in the winter solstice, which is out here, which means it makes a big circle. Now, let me explain to you how that works. Okay, I'm going to turn the light off on this phone for just a second so you can see how this works. Okay, here we are. I've gotten it dark like it would appear in real life. Now, we're going to use this flashlight as the sun source. Now, in the wintertime, the sun is further out, which means, okay, here's the ice wall that surrounds the Earth. Let me get you guys familiar with this really, really quick because I don't have a whole lot of time. Now, here's North America. Here's South America, here's Africa, here's third world countries, and here's Australia. Now in the wintertime, the sun is out here making its circuit around the Earth. And it never changes up its speed. It's always going the same speed. But being that it's further out, it takes a longer time for it to come back around. That's why in the wintertime, your nights are longer than your days, because it takes the sun a longer amount of time to get all the way back around. Now, as the months go by and it starts to get into spring, well, guess what the sun does? It starts to move back in on its circuit. So that's why, notice when the sun starts to move in, see, say this is the daytime in America, which is right here in the summertime. Well, you have daytime there. Well, check this out. In the spring, the sun starts to move closer in. So guess what starts happening to this continent and this continent and this continent? Well, it starts to get warmer because the sun's moving in. That would be your spring. So now, let me fast forward really quick. In the summertime, the sun is all the way in here. Now, that's why your days are longer, because it doesn't take the sun very long to get back around to you. So the nights are really short and the days are longer. Doesn't mean the sun's moving faster, it's just on a shorter circuit. Doesn't take long to make that circle when it's making a small circle. You guys see what I'm saying? So in between the winter solstice and the summer solstice, you have this in-between time, which is right in here. Well, in the summertime, it's really, really hot here in America. Okay, so in the fall, well, the sun starts to move back out. So this in-between right here, this is your spring and fall. This in-between time when the sun starts to move back out, guess what? It starts to get colder because it's moving further away from you. Now, notice everybody's like, oh, well, the southern countries are always hot. Well, it's really, really simple. You got South America, you got Africa, and you got Australia, and it's usually always hot in those areas. You know why? Because they're usually always under the sun as it's moving back and forward on its yearly circuit around. Now, it's really, really simple, and that's how your seasons work. In the summertime, it's a small circle, just like this right here. That's why your days are longer and your nights are shorter. Well, when the sun moves back out, notice how your days start getting shorter. That's because the sun's starting to make a bigger circle. And then in the wintertime, your nights are really, really long and your days are short, because it takes the sun a long time to bring its light back around and its heat back around. But its heat is way out here, and that's why it's cold here in the wintertime. But say in South America or Africa, it's not really cold in any of those months, because the sun is always over them, no matter if it's here or no matter if it's here. It's always over these countries. Now, your midnight sun, which is a 24-hour sun, and I think that for 187 days, which is a little over 4 months, which makes sense. You know, a summertime is about 3 months, a little over 3 months long. So as it fades back out, well, now, here's my point. If you're in the North Pole has 187 days of daylight, okay? Well, it's really, really simple. Look at the North Pole. This is the North Pole. In the summertime, the sun's on its short circuit, so guess what stays lit up the whole time? Even though the other countries over here are dark and the United States is lit up in the daytime, these countries are dark. Well, guess what's still lit up? The North Pole, the Arctic. No matter where it is, its circuit is so short, it keeps it lit up the whole time. And then you have 163 days, I believe it is, of darkness in the North Pole in the wintertime to us here in the United States. So in the wintertime, guess where the sun is? It's out here. So look at the North Pole. For all those months, it has no light because the sun is out here making its circuit. It's really, really simple, guys. I want you to understand how to read this map. And right here
It's very, very simple. That's why it says right here, longitude and time calculator. This tells you how the months work, and it tells you how the time works. Now, up here you have the morning, and over here you have noon, and right here you have evening, and right here you have midnight. So notice in Roman numerals how it goes 1 all the way over to 12, and then it starts over again, 1 all the way around to 12, because half of the earth for 12 hours is lit up. So let's say from morning all the way around here to evening. Well, over here it's midnight. That's why it says midnight there, because it's dark there. The sun is on this half of the earth, and then when it moves to this half of the earth, this half over here is dark. That's why it's numbered the way that it's numbered: morning, noon, evening, and night, midnight. That all the ancients knew this for years and years. And that's why this map, if you look at the very top, it says scientifically and practically correct as it is. Now, if you're wondering why the map says time calculator, well, it's really, really simple. For thousands and thousands of years, all the ancients used a sundial to tell the time. Okay? Now, you have to remember this. They even taught you this in school, that the sundial was used to tell time. Now, if we use a spinning ball, and the sun, it doesn't work. But I'm going to show you how this works. Check this out. It's really, really simple. Okay, hold on just a second. Okay, we're going to use this pencil right in the center of the earth at the North Pole as our sundial. And I'm going to show you that why this says time calculator. Now, let's say this is the sun, and remember the sun revolves around the earth clockwise. So here's our shadow from the sundial in the center of the earth. Now, as the sun makes its rotation, watch what the sundial does. What's it do? It tells the time: 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock. As the sun makes its circuit, that's how the sundial works. You see where I'm coming from? Now, when it's dark over on that side of the earth, it's light over here. You see, the sun has to make that circuit to make that sundial work. It's really, really, really simple, guys. Really simple. That's the only way it can work. The sundial does not work on a spinning ball. So if it doesn't work on a spinning ball, then that should tell you that the earth's flat. Either the earth is not flat, and for 5,000 years people were telling time the wrong way. And I don't think that that's very possible at all. Thanks for watching, guys. Most common questions I am asked is, how does an eclipse work on a flat earth? Well, to be honest, it's really complicated unless you understand how close the sun and moon are to the earth and the path that they take. Now, NASA and science tell us that an eclipse occurs when the moon gets between the earth and the sun, which is true. Now, let's give NASA the benefit of the doubt and test their theory really quick. The sun is supposed to be 400 times the size of the moon. Okay, so here I have a flashlight representing my sun source and a penny representing the moon. And as you can see, the flashlight is a lot larger than the penny. Okay, now let's place the sun 93 million miles out into space like this. let's get our penny a lot closer to the camera. Okay, where it's about the same size as the flashlight in perspective. Okay, now that doesn't look right. You can't see the corona, and it just doesn't eclipse. You can still see it light all around. It's not a total blackout like you see here in the 2017 total eclipse. Okay, now you guys seen that. That just did not look like an eclipse at all. Okay, now I have a side light on the side of this flashlight that just so happens to be the exact same size and diameter as the penny, which is perfect for our next test because the sun and the moon are the same size on a flat earth. And we'll bring the sun in closer to us as it would be on a flat earth. Now let's try our eclipse with the moon right underneath the sun. And wow, there's the corona. That was fabulous. Now let's compare the 2017 eclipse with the demonstration that I just showed you. That was really, really close, almost identical. Okay, now I'm going to show you how the eclipse works on a flat earth. The sun and the moon are kind of like the minute and the hour hand on a clock. The sun being the minute hand and the moon being the hour hand. The sun will eventually pass over the moon as the minute hand will eventually pass over the hour hand, causing what we see as an eclipse, as you can see right here in the illustration.
In just a few hours, the moon will pass completely in front of the sun, that event called totality, casting a shadow about 70 miles wide. The so-called path of totality spanning 14 states from Oregon to Charleston, South Carolina, where we find World News Tonight.
Now I'm just going to show you really quick how the eclipse went from the west coast of Oregon to the east coast of South Carolina. Now, as you know, the sun rotates around the earth in this circuit. Now we're going to use the penny as the moon, and I'll show you as the sun moves across the penny, it causes the shadow across the United States in the same pattern that the lady just showed you on the news. And that's how the eclipse works. Thanks for watching, guys. Good afternoon, everyone. Just wanted to do a really quick video on the sun speed because it seems like there are still a lot of people who do not understand the speed of the sun. A lot of people think that the sun has to speed up in its winter solstice, and it doesn't, of course, and I'm going to prove that to you right here with the Hammond's Air Age Map of the World, which is an old map the Air Force used back in the day. As you can see here, the white ice wall says Antarctica. You can see the time zones. If you go down here at the bottom, you'll see it again, Antarctica with the time zones. Perfect white ice wall all the way around. If you look at these little red lines,
all over this map. These were the actual flight routes in 1903 when this map was made. But what I'm going to be showing you here is how the sun revolves in a circuit around the flat Earth, just like the hand of a clock. The only difference is in the summertime the sun is lower in its summer solstice, so that's why you see this mechanical hand that I've made look like this. And up here is the sun in the wintertime. The sun ascends upward higher in the air in the winter than it does in the summer. That's why it's a lot colder in the winter. The sun is higher away from you and it's further away from you. So I'm going to demonstrate to you how the sun ascends in its winter solstice and descends in its summer solstice. All the while it's making its circuit around the flat Earth and keeping the same speed all year round. Just like when I hold this flashlight close to the floor, you have a small circle of light, but it still moves around in a circle at the same speed. Now, in the winter solstice, the sun ascends higher into the air and its light covers a larger area as the sun makes its circuit, but it still comes back around to its starting point within a 24-hour period. Let's turn the lights out. Now, as you can see here, when I cover this light, this is your summer solstice right here. It's very small circuit and very close to the Earth. Now, watch when I cover the summer solstice up. Now, here's your winter solstice. The sun is higher, so therefore it covers a larger area. Okay, now here is your summer solstice right here. Notice how it makes a small circle and the light is very bright and close to the Earth. Okay, now here is your winter solstice. This is when the sun ascends higher and moves further away from you. Now notice how much of a larger area that its light covers in the winter. That is how the sun still makes its circuit within a 24-hour period. It doesn't change its speed, it simply raises up higher and its light spreads out further. Now here I'm demonstrating the summer solstice and the winter solstice at the same time. Notice the summer solstice is closer to the map and it's brighter and makes a small circle. And notice the winter solstice is higher and its light covers a bigger distance. But the sun still completes its circuit within a 24-hour period. Just like this second hand I told you before, whether the sun is at the tip of the hand or at the center of the hand, it still will complete its circuit within a 24-hour period. Just like this hand on this clock will complete its circuit within 60 seconds. That's called angular speed, which gives the rate at which the center angle is swept out by the object changes. The object moves around the circle and is thus measured in radius per unit time. Now I'm going to show you my demonstration along the side of clock. I'm going to show you that the hand on the clock and the hand on the map that I made, they both reach the 12 o'clock position at the same time. The center of the hand and the tip of the hand reach the end of its circuit at the same time. It does not change its speed. The only thing that changes is the sun's light, because it ascends up and it ascends down as it makes its circuit. And it's as simple as that. Thanks for watching and God bless. Now, as you can see here, the sun rays are coming out right here to the left at around a 7.2 degree angle. Now, right here in the middle, they're coming straight down. Now, when you get back over here to the right, they're coming back out at a 7.2 degree angle. Now, a little bit of calculation will show that a 7.2 degrees on each side coming up to a perfect triangle puts the sun at about 4,000 miles up into the sky. Now I'm going to prove that to you really quick. Here I have a piece of cardboard that I have cut the edges out perfectly on the edge of this cardboard. Now over here we have a flashlight And if you look right in front of the flashlight, you will see a perfect 7.2 degree triangle leading right to the edge of the flashlight, the light source itself. So when you look up into the sky and you see where that triangle comes up and meets to a point, that is where your light source is located. So like I said, we have this flashlight in which we're going to use as our sun source. Now, let's go over here and turn the light out. Now, check this out. Notice that the shadow of the edges of the cardboard are parallel with each other. That would be 93 million miles away. They'd all be parallel with each other. Now, let's watch what happens to the shadows of these edges when I move them in close to the light source. Remembering that the piece of cardboard represents our cloud. Now about right here is a 7.2 degree angle. Now if you don't understand this, apparently you failed science and physics. This right here proves that the sun is only about 4,000 miles up in the air, just right above the clouds. That's the only possible way to get crepuscular sun rays. Anyways, I'll let Professor Leo Ferrari explain it to you simply.
Does running round your neighborhood prove that the neighborhood is round?
Dr. Leo Ferrari explains.
Oh, the Eratosthenes experiment is an experiment supposedly conducted in the 1st century, whereby this ingenious person was supposed to have proved, I say that in quotes, that the Earth was a sphere of some 4,000 miles radius. Eratosthenes one day noticed that the sun was directly overhead in Syene, whereas he noticed that on the same day, at the same time, the sun made an angle of 7.2 degrees to the vertical at Alexandria, which was some 530 miles away. How did Eratosthenes in the 1st century know what the sun was doing on the same day in two places which are 530 miles apart? One can take all those same data, knowing that the Earth is flat. In one place you have the sun directly overhead, and at another place, at the same time, at 530 miles away, let us suppose that it does make an angle of 7.2 degrees to the vertical. Then we have a right-angled triangle, which it can be easily shown that the sun is some 4,000 miles up in the sky. With a sphere of 4,000 miles radius, being spun round once every 24 hours, a little bit of calculations will show that that person there is being spun round at about 1,000 miles an hour and it doesn't know it. I mean, this is obvious nonsense. You go on a merry-go-round and it goes, I doubt, more than 10 miles an hour, and you get off all dizzy. You mean to tell me that people can be spun round at approximately 1,000 miles an hour and not know it? Why, if this is so, this whole room that we're in is supposedly being spun round at something of approximately that order of speed, and we don't know it. Superficial, even, considerations show that it's impossible. The whole thing, it's a story, a fairy story made up and mindlessly repeated in textbooks.
Fredericton author and teacher Leo Ferrari died this week. We last spoke to Leo Ferrari in April of 2005. He had Alzheimer's disease. He spoke about what was happening to him at every opportunity, including an attempt to slow the process with the drug Aricept. He and his partner, Lorna Drew, wrote about the subject, offering suggestions for others entering into that world. Ferrari was a retired scientist, philosophy professor, and world-renowned authority on St. Augustine. He is the author of numerous scholarly books and 2 collections of poetry. Ferrari passed away on Tuesday in Fredericton. He was 83.